All right. So our fourth and final objective is to understand regulation and control of the cardiac output. So just to recap what we've discussed so far, we've talked about the anatomy of the heart. We've talked about the various structures, the chambers, the valves, the flow through the heart. We talked about the electrical activity of the heart, the pacemaker cells, which kind of set the rhythm, the contractile cells, which sort of distribute that and contract the chambers. We've talked about how the electrical impulse moves through the heart. And then most recently, last week, Friday, we talked about the cardiac cycle. So how a single heartbeat relates to each of those events, how we have ventricles contracting, atria contracting, and then ventricles relaxing, and then atria relaxing. So we talk about the events in a single heartbeat, those different phases. And so what we'll do now is really put all of that together and talk about how that is regulated. So how do we speed up the heart rate? How do we slow it down? What are the hormones that are involved? What are the divisions of the nervous system, so the sympathetic, parasympathetic, and how does that affect the heart rate and rhythm? So we'll talk about the regulation and control of the cardiac output. And we want to begin by looking at a practice question here. So I'm going to launch a poll just to sort of prime ourselves. Another 5 seconds. All right. Given what you know about how we control the contractile events in the heart, which branch of the nervous system do you think affects the heart? Oh, I didn't realize there was no option E. Good point. Thanks for letting me know. That definitely affects how we can answer this question. So yes, the answer is actually E, and unfortunately there was not an option E. But let's just talk about the question here. So the branch of the nervous system that controls the heart rate would be parasympathetic and sympathetic. So that would be the autonomic division, right? Because this is cardiac muscle. This would be controlled by those two divisions of the nervous system. And not the somatic, right? Somatic would be our skeletal muscle that would be voluntarily controlled. Okay, so E was the correct answer here. So let's first start by defining cardiac output, and then we'll talk about some parameters that can regulate cardiac output. So cardiac output is a rate. That's the first thing we want to understand, is that it's not just a volume of blood, but it is a volume of blood with time. So it's a rate. So it is the stroke volume, which we know to be the amount of volume that leaves the ventricle, that is ejected from the heart, and specifically that volume with the heart rate. So it's the stroke volume times the heart rate. So it is telling us how much blood can be distributed specifically from, it can be calculated from both of the ventricles, but usually when we talk about cardiac output, we're usually referring to the left ventricle and the output from that chamber. Simply because the left ventricle is going to supply the blood that gives supply to our entire systemic circulation. So we typically discuss cardiac output as a product of left ventricle, but it can be calculated on both sides. And so it is our stroke volume, the amount that is ejected from the ventricle, times our heart rate. Why do we multiply it by the heart rate? Because we want to take into account how fast or slow the heart is beating, because that will determine how much time there is for filling and how much can be ejected in each heartbeat. So the average cardiac output is about 5 liters per minute at rest. So as you're casually sitting, your body is delivering 5 liters of blood every single minute. That's really an astronomical value to appreciate, right? And if we think about the average blood volume, how much blood is sitting in our body, typically for a typical average size adult, that's about 5.5 liters. So what this tells us is that in every single minute, our heart can mobilize all the blood that's in our body, right? Which is even more fascinating. So our cardiac output is about 5 liters per minute while we're resting. It can go way higher than that, depending on our state of activity. While we're exercising, it can bump up to 6, 7 liters, but it can equal our entire blood volume even while we're simply resting. Some of the factors that affect the cardiac output are going to be the two variables, right? We know that it's heart rate times stroke volume. Therefore, anything that influences heart rate will influence cardiac output. Anything that influences stroke volume will influence cardiac output as well. The ways that we can regulate this are extrinsic mechanisms and intrinsic mechanisms. So when we say extrinsic mechanisms of regulating the cardiac output, we're talking about neurons, we're talking about hormones, we're talking about anything that's external that can be applied to the muscles of the heart, whether it be the contractile cells or the pacemaker cells. And that would be your parasympathetic and sympathetic influence. Those would both be considered extrinsic. Intrinsic modes of regulating would be autoregulation. So we will speak about some aspects of cardiac function that are auto-regulated, where the heart will automatically have a certain response just based upon its natural anatomy or physiology. A good example of this right off the bat is if we think about the stretching of the cardiac fibers. If we stretch the cardiac fibers more force is generated so that the heart works harder simply by stretching more. In other words, if more blood comes back into the chambers, that causes a further stretch and that results in more force generation. So that would be an example of intrinsic ways in which the heart can regulate its own cardiac output. Just to illustrate how those factors, those structures receive input, external input, we've got the nervous system here on the left, right? The brain, parts of the medulla, which have some of the cell bodies of our parasympathetic neurons. So for example, the vagus nerve would have its cell bodies in the medulla. It will project its axons all the way out to innervate the cardiac muscle cells, specifically the pacemaker cells of the heart. So notice that the blue arrows, blue lines here, which are representing the parasympathetic fibers within the vagus nerve, only go to the SA nodal fibers and then to the AV nodal fibers. Okay, that is to say that the parasympathetic system is really only having an influence on the pacemaker cells. The sympathetic influence, on the other hand, which is coming from our thoracolumbar spinal cord, synapsing briefly on the sympathetic chain, right? This anatomy we've talked about before, and then the postganglionic fibers of those neurons synapsing onto the heart. Now notice here, the sympathetic division synapse onto the pacemaker cells or the SA node, the AV node, as well as the rest of the cardiac myocytes, so the cardiac contractile cells, which are really found throughout the ventricles. So that is to say that the sympathetic nervous system has an influence on the pacemaker cells as well as the contractile cells, and we'll talk about why that's important as well. So what we will do at this point is we will talk about factors that influence both of those things individually. What are factors that will change the heart rate? And then later on, we'll talk about what are factors that will change the stroke volume, so that by the end of this, we will have talked about all the factors that change heart rate and stroke volume, which we know will influence cumulatively the cardiac output. So heart rate is determined by the rate of the SA node firing. How fast is that SA node firing in terms of its innate autorhythmicity? We know that if there is no extrinsic control, the SA node would fire at about 100 action potentials per minute. So if you were to take an SA nodal cell and you were to put it into a Petri dish and you were to allow it to generate action potentials of its own doing without any type of extrinsic influence, it would generate 100 action potentials in every minute. Now, because the way that the SA nodal cells in our body are under the influence of sympathetic and parasympathetic, also because at rest, there's slightly more of a predominance of the parasympathetic, our heart rate is not going to be as fast as 100 beats per minute at rest. At rest, our heart rate is going to be closer to about 75 beats per minute because that parasympathetic system slightly slows down or dampens the excitability of the pacemaker cells and brings that from 100 to about 75 in our body at rest. If we are excited, so if there's some type of excitement happening, if there's the sympathetic response at play, then the sympathetic will increase that firing rate, and that will bring our heart rate closer to about 100 beats per minute. All right, so there is this comparative secrecy. We've talked about this before, where we've got parasympathetic bringing things down, sympathetic bringing things up, and just the balance of those two inputs can affect our heart rate. So here's what that will look like. If we have increased sympathetic activity, we have increased epinephrine being released from the postganglionic neurons. We've got beta-1 receptors, right? We know that the adrenergic receptors that are specific to cardiac muscle are called beta-1 receptors. They are specifically on the SA node and AV node. What's going to happen is we're going to increase the opening of sodium channels, of calcium channels, and that is going to increase the rate of spontaneous depolarization on those cells. Now, if these cells can spontaneously depolarize faster, then they are going to generate a faster rate, and that is going to result in an increase in the heart rate. Okay. So here is a schematic that illustrates this. So we've got our beta-1 cell on our cardiac muscle SA node, with our cardiac SA node cell, excuse me. We've got norepinephrine or epinephrine binding here. It's coupled to this G protein. That results in increase in our second messenger. And the results that are brought about by that increase in second messenger is increased opening of funny channels and an increased opening of T-type calcium channels. Now, we've talked about the events or the ionic movement that brings about depolarization on a pacemaker cell. It's going to start with the funny channels opening up, which creates a net movement of sodium. And then it's going to result in calcium channels opening up, and that's going to bring about the rapid depolarization in a pacemaker cell. So if we can have these events coupled to the binding of norepinephrine to this beta-1 receptor, and if we can increase the rate of that, we can increase the rate of pacemaker potentials firing their action potentials, and this results in increasing the heart rate. All right, so this is just reviewing the underlying mechanism of why the sympathetic nervous system increases the heart rate in pacemaker cells. Let's look at those similar events, but in the opposite direction. Here we're looking at how the parasympathetic activity by way of the vagus nerve can actually encourage the muscarinic cholinergic receptors, right? So acetylcholine will bind to these muscarinic cholinergic receptors on the SA node. That will increase the state of opening of potassium channels and close the state of calcium channels. Guess what this does? If we open up potassium channels and close calcium channels, we make it harder to fire an action potential. If we have more potassium moving, that's going to be more towards repolarization. If we don't have calcium moving, it's harder to encourage that rapid depolarization. So by way of doing these two things, we make it harder to depolarize the cell. In other words, we hyperpolarize these pacemaker cells, and we decrease the rate with which action potentials can be fired, and we decrease the heart rate. So notice how The parasympathetic system, by way of these muscarinic receptors, can make it harder to depolarize pacemaker cells, whereas the sympathetic system, by way of the beta-1 receptors, can make it easier or more favorable to fire action potentials and can increase the heart rate. Okay, here's the mechanism for the parasympathetic side. So we've got the T-type calcium channels. These are closed, so it's harder for calcium to get into the cell, as well as potassium channels, which are now wide open. So that's allowing potassium to leave the channel. We know that potassium is positively charged. We know that if more potassium leaves, that is considered a hyperpolarizing event, and that's going to just decrease the amount of positive charge in the cell, right? Both of these events will do that, which makes it harder to depolarize, which makes it harder to fire an action potential, which makes the heart rate slower. Okay, so this is the mechanism by which the parasympathetic system slows down the heart rate by decreasing the depolarizing events on pacemaker cells. Here's a graph comparing what both of those different events look like. So notice we've got the resting event, which is in gray. This is the rate at which a pacemaker cell would fire action potentials at rest, which is in this span of time, we've got 2 action potentials fired. If we had the parasympathetic system exerting its influence, we would have only 1 action potential fired in this span of time. On the other end of the spectrum, if we had more of that sympathetic influence having effect, we would have 3 action potentials fired in this exact span of time. So notice how the parasympathetic system decreases the firing rate of the pacemaker cells, and the sympathetic system increases the firing rate of our sympathetic or SA nodal cells. So that was the first effect, right? The neuronal input on our heart rate. The second effect is slightly similar. This is how hormones can influence the heart rate. Specifically hormones like epinephrine, which we know mimic the sympathetic nervous system. They have the same exact effect. The only difference is the type of molecule that's bringing that effect about. So in our neuronal example, this was neurotransmitters that are binding to these receptors and bringing about this effect. In the hormonal version of that, it's just epinephrine acting as a hormone circulated through the blood, also binding to those exact same receptors and bringing about the same effect, which is to increase the action potential frequency. And then it also will increase the speed of the action potential conduction that moves throughout the rest of the muscle as well. Glucagon is another hormone that influences our heart rate. Glucagon is going to increase the rate at which our heart muscle pacemaker cells fire action potentials, which will increase the heart rate. And so just to point out here that this is an integration. So both these divisions are projecting onto the heart rate. SA node is trying to speed it up. Sympathetic nervous system is trying to speed it up. Parasympathetic nervous system is trying to slow it down. And then we also have various levels of hormones that are circulating in the blood that would also be working to raise the heart rate as well. So there are several different components that are acting on the heart rate, and it really just depends on which of them have the predominant influence that would determine which direction the heart rate is changing. All right. So that is looking specifically at just one variable of our cardiac output. What are the things that influence heart rate? And just to recap what we said the sympathetic system, the parasympathetic system, and then hormones such as glucagon and epinephrine as well. The second variable here is our stroke volume. So let's look at some of the factors that will influence our stroke volume independently. And so these are also variables that will collectively influence our cardiac output as well. So the things that influence stroke volume are the ventricular contractility. That means how hard are the contractile cells of the ventricles working? How much force are they generating? The second is the end diastolic volume. That is how much volume has filled into the ventricles at the end of diastole. That will definitely affect how much can be ejected. We've mentioned this before. If the heart can fill adequately, it can certainly eject adequately. So the amount of volume that was filled at the end of diastole will certainly have a role in determining how much stroke volume is ejected in that from that chamber as well. The last factor is the afterload. And afterload is basically how much pressure exists in the systemic circulation, in the systemic vasculature, against which the stroke volume has to compete, right? Afterload is basically how much pressure exists in our systemic vasculature. And so that is going to play a part in the stroke volume because the stroke volume has to work against any peripheral resistance that exists in our systemic vasculature. Okay, so these are our three factors that will influence stroke volume. Now, let's start with the first one, which is the ventricular contractility. If the heart is beating more forcefully, it will expel more blood, okay? Therefore, if there's more of a sympathetic influence, which will encourage more forceful ventricular contraction, then that will encourage more stroke volume to be ejected from that chamber. So the sympathetic system, by way of norepinephrine binding to, once again, our beta-1 receptors, more of that cyclic AMP being released, that will encourage 4 events that will result in increased ventricular contractility. All right, what are those 4 events? It's going to augment the time that the calcium channels are open, which will simply allow more calcium to flood the sarcoplasm in our cardiac myocytes. It will increase the amount of calcium that's released from the SR, right? Remember, cardiac and smooth muscle have 2 sources of calcium that is important for their contraction. Skeletal muscle, we said, only had calcium coming from the SR. But for cardiac and smooth muscle, they have calcium coming from the SR. They also have calcium that's coming in from the external, the extracellular fluid as well. So opening up those calcium channels in both of these spots will simply increase the amount of calcium that will increase the force generation. The third point is increasing the myosin ATPase rate. If our myosin heads can move at a faster rate, then they can increase their force of contractility. And then the fourth factor is to enhance the calcium ATPase pump, which pumps calcium back into the SR. And we talked about this phenomena. If we can clear the calcium from the SR more quickly, we can cause the muscle to relax more quickly, and we can stimulate another contraction more quickly. So the rate of relaxation also increases the ventricular contractility. All right, so let's illustrate those 4 events that are increased by the sympathetic activity. So the opening of our calcium channels to allow more calcium to come in from the extracellular fluid, that is increased. The opening of calcium channels that are on the SR, that will allow more calcium to be dumped from the SR into the sarcoplasm, that will also be increased. The myosin ATPase rate on the myosin heads, right, if they can be moving faster, that will increase the ventricular contractility, how much force is being generated by these cardiac cells. And then lastly, if we can increase the calcium ATPase pump on the SR, in other words, pumping more calcium back into the SR to allow the muscle to relax more quickly, then that will also increase the rate and the contractility of these cells as well. All right. Okay, so now if we can compare the tension or force production, and remember here, the tension is how much force the cardiac muscle is contracting with. And if the cardiac muscle can contract more forcefully, it can expel more blood. So that is the connection with our stroke volume. So more tension or force production results in more stroke volume. And so that's the connection that we're really targeting. So if we have more force generation, right? That is happening under the influence of the sympathetic activity, and that is happening in a shorter duration of time. And if we can compare that to what's happening at rest, we'll see that much more force is being produced when the cardiac muscles contract under the influence of the sympathetic nervous system than the amount of force that's being produced when these muscle cells are at rest. Okay. Now, the second part of this is looking at the parasympathetic system. And here's where I'm going to have a huge exclamation point, because this is something that's really important to remember, is that the parasympathetic system does not have any influence on the contractile cells. So I mentioned this earlier, but I'm going to just reiterate it here as well. And if we just look at the neurons that are projecting, that are parasympathetic, they are only going to the SA nodal cells and then to the AV nodal cells. They are only influencing the pacemaker cells. The parasympathetic does not have a significant influence on the contractile cells of the ventricle. In other words, the parasympathetic system is really only manipulating the heart rate. How fast or slow are these pacemaker cells initiating the rhythm? It is not going to have as much of an effect, if any at all, on the force of contractility that is found in the contractile cells of the ventricle. All right, really important to remember that. Lastly are the hormones. So what are the hormones that can influence stroke volume by way of influencing the contractility? And that would be simply the epinephrine hormone, which is again mimicking the sympathetic nervous system. So by way of epinephrine as a hormone binding to beta-1 receptors, we get those same four events that are augmented when the neurons are innervating the cardiac myocytes, right? So the increase in the weight of the calcium channels on the SR, as well as on the cell membrane, increase in the myosin ATPase activity, as well as increasing the calcium ATPase activity on the SR. So those same four events are going to be brought about when it's a neurotransmitter as they are when it's a hormone. The other hormones at play are insulin, glucagon. Both of these hormones can increase the force of contraction of the heart as well. And so they would also help to increase the stroke volume. And then thyroid hormone. I think I missed the thyroid hormone. All right. The second part of the equation here is the end diastolic volume, right? So this is another factor that can influence stroke volume. And end diastolic volume is simply how much volume has filled into that ventricle. So this brings us to speaking about Starling's law. And Starling's law is if we can increase the end diastolic stretch, we can get these fibers and get the sarcomeres closer to their optimal length, and they can generate more force. All right. And I'll sort of expand on this because it's really important to contrast this to what we described as the optimal length for skeletal muscle. In skeletal muscle, the sarcomere and the fibers are usually at their optimal length when they're at rest. Okay, we talked about skeletal muscles being suspended across a joint. And so the sarcomere was typically at its optimal length. And so it would generate the maximum amount of force at that nice medium sort of intermediate length. If we were to stretch the sarcomere too much, we would decrease the force generation. If we were to contract the sarcomere too much, we would also decrease the force generation. So that was for skeletal muscle. For cardiac muscle, it's different. For cardiac muscle, the further away we stretch that sarcomere, the closer we get to the optimal length. And so the further away we stretch that fiber, the more force we'll generate. Okay, so for that reason, whenever we stretch the ventricles so that they can accommodate more volume, the fibers are stretching as well. The sarcomere is stretching as well. And guess what? We have more force generation that's being captured in that ventricle. And so when that chamber does contract, it's going to do so more forcefully. That phenomenon is called Starling's law, right? So the result of that is going to be increase of the force and then increased blood being propelled from that chamber. So this is why I keep emphasizing this relationship that if the heart can fill adequately, It can stretch the fibers, which can result in more force being generated in those contractile cells, which will propel the blood further, and that will result in more stroke volume leaving that chamber, okay? So increased venous return results in increased stretch. That results in increase in the strength of the contraction simply by bringing those fibers closer to their optimal length, and then that will result in increased stroke volume or increased volume of blood being ejected from the chamber. All right. Okay, so here is what that looks like, just an illustration here. Let's see. Excellent, excellent way to phrase this. The harder that it is stretched, the more force we will get. Excellent way to change this concept. So that's Starling's law concept. The harder that we can stretch that muscle, and what's stretching it is really the volume of blood that's coming back, right? The volume of blood that's coming back into that ventricle will stretch that chamber more, which will stretch the muscle more, which will mean it's going to contract more forcefully when it does contract, and it's going to expel more blood simply because it has stretched harder. All right, perfect. So just to illustrate that here, so here is the amount of blood that was filled at rest, and then the amount of blood that was ejected at rest, right? Our end diastolic volume here, and then our stroke volume here at rest. Notice that the point of the sarcomere is more contracted in this state, all right? If we had more end diastolic volume, right, we would stretch the sarcomere larger. So notice how in this view, the sarcomere is extended or stretched just a little bit more. And notice how we all of a sudden extend or expel much more stroke volume, right? So the more volume we fill, the more we stretch the sarcomere, and the more forcefully we can contract, which results in more stroke volume. Okay. And then another illustration to emphasize that. So here is our curve at rest. Stroke volume versus end diastolic volume versus our stroke volume. Here is our curve if there is an increased sympathetic activity, right? Much higher stroke volume for the same amount of end diastolic volume, right? Simply because we have more of that sympathetic influence onto the ventricular contractility. And then here's our stroke volume if we have decreased sympathetic activity. Okay, so there is less of that stroke volume because we have less of that sympathetic influence, which is bringing about those four events. So we have less of the calcium channels being open, less of the myosin ATPase activity, less of the calcium ATPase activity, which brings our stroke volume down, even for the exact same end diastolic volume. Okay, what are some factors that are affecting the end diastolic volume? Okay, so great question here. Let me just jump back. Why doesn't the volume change? So the volume doesn't change in this example, and this example is really highlighting how Starling curve changes based upon the sympathetic input, right? Based upon the sympathetic input only. So the phenomenon that we describe, which is Starling's law, is going to change if the volume does change. That is true. But even if the volume didn't change, simply because of these extrinsic or external factors that are influencing the heart muscles, right, that are going to bring about those four changes that we talked about, the stroke volume would still increase simply because of the sympathetic influence. Okay, so we can show here that even if we are not allowing the heart more time to fill, we can still, by way of these external influences, increase the amount of stroke volume that we get. All right, okay, hope I answered that question. Okay, we are running out of time, so let me just try to wrap this up. And I will just have to post a recording for the review just because we're running shorter than I expected on time. So factors that are affecting the end diastolic volume here are going to be the preload, and preload is basically the pressure with which blood is coming back to the filling chambers, right, coming back to the atria and then subsequently the ventricle. So this is really the pressure with which the blood is coming back or filling. That can further be influenced by the filling time. If the heart is allowed adequate time to fill, we're going to have more of that preload coming back. We're going to have higher pressure coming back. This is also influenced by the atrial pressure, right? How much pressure is being exerted by the atria. Remember, when blood comes back from the veins, it has to go to the atria and then down into the ventricle. So if there's higher pressures being exerted in the atria, blood is going to move more forcefully down into that ventricle, and that's going to influence our end diastolic, how much volume is filled in that chamber as well. The third one is the central venous pressure, and this is the amount of pressure that's existing not in the atria, but out in those venous structures, our central veins, our systemic veins, for example, our superior vena cava, our inferior vena cava, our pulmonary veins. How much pressure is exerted in those vessels? That's called our central venous pressure. And if that blood is returning to the heart under tremendous pressure, that will also encourage more blood to be filled into our ventricle as well. So these are some of the other factors that will influence how much blood is filling at the end of diastole into the ventricles. The last factor is really our afterload. And afterload is the pressure that is in the vessels that are away from the heart, right? So preload is the pressure within the vessels and the structures that are coming into the ventricle. Afterload is the pressure in the structures and the vessels that are leaving that ventricle, which is mainly the aorta for our purposes. So what does the pressure in the aorta look like? What does the resistance in the aorta look like? Do I have a lot of peripheral resistance? Because then that means it's going to be harder for me to eject more blood out into that systemic circulation, and I'm going to have more blood sitting in my ventricle at the end of diastole and even systole. So the pressure that's exerted in the distal structure is just as important as the pressure that's exerted in the proximal structures, and both of those will influence how much blood has filled into the ventricle at the end of diastole. All right, and that will subsequently influence how much can be ejected as our stroke volume. Okay, here's a schematic just illustrating, this is just for the stroke volume. So what are the factors that are affecting the stroke volume? So our venous return being the main one here. And this is tying into preload. So you can write preload here on your notes because it's sort of the same thing. How much blood is coming back from the venous structures, superior vena cava, inferior vena cava, that influences how much is filled into our ventricle. The sympathetic activity is going to influence the contractility, right? So this is also going to influence how much blood can be ejected, right? Because we're going to change how hard the heart is working, and that will change how much can be ejected as our stroke volume. And then the afterload, how much peripheral resistance or pressure exists in our distal vessels, right? So our aorta and beyond. How much pressure exists in those vessels, and that will also influence our stroke volume. So if we decrease the pressure in those vessels, we will increase how much can be ejected, right? We'll increase our stroke volume. If we increase the contractility of the heart, how hard those contractile cells are working, we will increase our stroke volume. And if we increase the end diastolic volume, how much blood has filled into that ventricle, we will also increase our stroke volume, which is how much can be ejected. All right. Okay. Let's do one practice question. And then as I mentioned, I will share a full recording going over what is important for the exam on Wednesday. So let's just launch a poll here. All right. So cardiac output decreases with decreased stroke volume. All right, you can see the rest of this. And heart rate. How do sympathetic and parasympathetic activity act? So most of you picked C. Decreased sympathetic activity decreases stroke volume and heart rate. Increased parasympathetic activity decreases heart rate. All right, so that is absolutely correct, okay? I'm glad that no one went with B or even A, right? Because we know that the parasympathetic activity only decreases heart rate. The parasympathetic activity has zero influence on stroke volume, right? There's no influence of parasympathetic stimulus on the contractile cells. It is only going to be increased by sympathetic activity, and then it's going to be decreased when sympathetic activity decreases, okay? So C is correct. All right. So I'm gonna call it a day here for today. Again, I'm gonna post a recording, but I just wanna quickly list some of the topics that I wanted to review. If you have follow-up questions on these, please let me know. But we talked about the factors that affect force generation, right? So the cross-bridge cycling, right? The optimal length, the frequency of action potentials, and then recruitment. We talked about the size principle when we talked about recruitment. So know that small fibers, small units, small diameters are recruited first. These are for smaller, more fine activities before large fibers, large diameters, large units. Lastly, we talked about the velocity of shortening. So this idea that heavier load requires a longer latent period, a decreased duration of contraction, and a decreased velocity of shortening. We then talked about the different types of ATP sources for muscle contraction. So the creatine phosphate system, the oxidative phosphorylation, and the anaerobic glycolysis. And then on that basis, we talked about the different types of activities. So light intensity activities, which simply have that creatine phosphate system, then anaerobic glycolysis, and then mainly oxidative phosphorylation. Whereas heavier intensity activities are going to have the creatine phosphate, oxidative phosphorylation, and then mainly anaerobic glycolysis, okay? We talked about the 3 muscle fiber types. So go over those 3 types. I think we looked at some really nice summary tables. Which of them have more mitochondria? Which of them have faster contraction? Which have more capillaries, more myoglobin? Which ones fatigue more quickly? Definitely review each of those parameters. And then for smooth muscle, we talked about the mechanism for smooth muscle contraction, so the calcium calmodulin complex, the role of MLCK in that, the myosin phosphatase and how that dephosphorylates the myosin head. So go over that mechanism. Also review some of the main differences between our 3 types of muscle. So between single unit, multi-unit, cardiac muscle, and skeletal muscle, what are the differences? Which of them have gap junctions? Which of them allow for recruitment? Go over those main differences as well. And then for the cardiovascular system, I think I reviewed most of what we talked about at the beginning, but certainly go over the flow through the heart, know what valves are encountered, what chambers are encountered, and then go over the electrical activity, the ionic basis in the pacemaker cell versus the contractile cell, go over the cardiac cycle, those 4 events, and then what we would have covered today, which is how the sympathetic system influences heart rate and stroke volume, and how the parasympathetic system influences mainly our heart rate. Okay, I think that is all for today, guys. Please let me know if you have questions, and I will see you on Wednesday for your exam. Good luck.